Hey, this is Professor Behrang. I am a mechanical engineering faculty. I am also a licensed professional engineer in the state of Washington. My area of expertise is thermal fluids. This video is about uncertainty propagation, how to calculate uncertainty propagation by hand and using EES both. So it's going to be useful because when the equations get really big, calculating uncertainty propagation by hand takes a long time. You're going to make mistakes. So first, we're going to go over the theory of it, where it comes from pretty quickly. And then I'm going to show you one example, and we're going to solve it by hand. And then we're going to solve this exact same problem using EES. So you learn both methods. So make sure you subscribe to this channel as I upload more videos in the area of thermal and fluids this summer. So usually I start every video with a problem. So I'm going to propose a problem, very simple problem. The problem is that, let's say we have a temperature sensor, a thermocouple, and we have a pressure transducer, or we have a barometer, something like that, to measure pressure. Let's say we're inside a room, right? And then you put a barometer and then you put a thermometer in that room, and you measure the temperature of that room. And using the ideal gas law, you want to calculate the density of air in that room. So the question is that if the pressure transducer is off by, let's say, 10 kPa, and the thermometer is off by like 2 degrees Celsius, then how is that going to affect the calculation of density? Because if those values that you measured are not accurate, the density that you're going to calculate using the ideal gas law is not going to be accurate either. So if the temperature is off by 10 kPa, the density is off by how many kilograms per meters cubed? That's the question. And that's called uncertainty propagation. Uncertainty propagation is basically when you measure something and using some piece of instrumentation, and that piece of instrumentation has uncertainty when you're measuring something, and then use an equation that basically uses whatever you measured to calculate a variable. And that variable that was calculated will have uncertainty because what you measured had uncertainty. So let's start with that problem, and let's go over the uncertainty propagation theory and then how to use it, how to solve the problem by hand and how to solve it using EES. Okay, so here's the problem. Let's say this is a room like this, and we put a thermocouple and let's say a thermometer and a barometer in this room, and we measure the value of pressure in the room to be 100 kPa plus minus 10 kPa, like this. And we measure the temperature of the room as 20 degrees Celsius plus minus 2 degrees Celsius, like this. So that's a problem. And we want to, based on these measurements, we want to calculate the density of the air in the room. We know that we're going to use the ideal gas law. So the equation is pretty simple. Ideal gas law says density equals pressure over RT. Well, we know that this pressure has to be Pascal. We're going to use basic SI units. Its temperature has to be Kelvin, and this R has to be joules per kilogram Kelvin. You already know these things. And eventually, if you use the correct values, density is going to be kilograms per meters cubed. Okay, so the average values are given. The average value of the temperature is 20 degrees Celsius, and the average value of pressure is 100 kPa. And there is uncertainty. The question is that, I can easily calculate the average value of, density. If I calculate the average value of density, what do I get? This is what you get. You're like, okay, rho is P over RT. First, I have to make sure that these values are in basic SI units. Then pressure would be 100 times 10 to the third pascals. R for air is 287 joules per kilogram Kelvin times temperature. Temperature has to be Kelvin, so that would be 20 plus 273.15. Now this temperature becomes Kelvin instead of Celsius. Now I can calculate the value of density. If you actually do the calculation, you realize, okay, the value that you're going to get already did that, is 1.189 kilograms per meters cubed. Again, the question is, okay, you want to report this value. What is, if I want to report this value, what would be the value of density? Density seems to be 1.189 kilograms per meters cubed plus minus what? The original values, the original values that I measured had uncertainty. So what would be the uncertainty of density using those values that were not exact, right? Were not that accurate. This is where the theory of uncertainty propagation shows up, basically. Now, so our question is how to calculate this uncertainty. How do I calculate that value? Okay, so we have to give you a little bit of background, maybe about 5 to 10 minutes maximum, and then we can solve the problem by hand and ease. So here's the background I'm going to give you. Everything that you measure, let's say pressure, let's say any parameter, let's call that parameter X. Any parameter that you measure, let's call it X, right? When you measure it, you're measuring the average values. Sometimes you measure it multiple times and then you take the average. You use some statistical methods to find the uncertainty, things that you learn in statistics. It's called the confidence interval, something like that, right? So you measure the average value after measuring it multiple times, you find the average, and you also report some sort of uncertainty. Let's show the uncertainty by W sub X. The example in our case is, okay, we measured two things. What did we measure? We measured pressure. Pressure was supposed to be 100 kPa, okay? And that's the average value, basically. And plus minus some sort of 10 kPa uncertainty or a confidence interval, whatever that thing is, that's the uncertainty of it. 10 kPa is the uncertainty of it. Same case with the temperature. The temperature that we measured was 20 degrees Celsius. That's the average value, plus minus 2 degrees Celsius for uncertainty. So if I want to report this, this is the equivalent of pressure equals the average pressure plus minus the uncertainty of pressure. And this is the equivalent of T equals T average plus minus the uncertainty of temperature, like this. What does that mean? It means that, the average, where the average value of pressure is 100 kPa and the uncertainty of pressure is 10 kPa. And I'm going to make sure that my face is not blocking anything that you see here. And the average value of temperature is 20 degrees Celsius, and the uncertainty of temperature is 2 degrees Celsius, like this. Okay. Now, covering this, the question is, what are we looking for? We're looking for density. Okay, so if that's density, the equation I'm going to use is density equals P over RT. In other words, density is just a function of three parameters: pressure, temperature, and R being the gas constant, the ideal gas constant. Okay. R is actually a constant number, so R doesn't have any uncertainty. So you would just treat it as a constant number in this case. You don't have to worry about it. Now, going back to the beginning of it, this can be applied to any function. You can have a function like f, and f could be a function of a bunch of different variables of x, x1, x2 to xn, right? In our case for density, basically, density was a function of two things because R was a constant number. So, or I can include R also. Density was a function of x1, x2, and x3, like this. And P being x1, T being x2, and R being x3 in this case, right? Now, what's the uncertainty of WX1? WX1 was given as 10 kPa, Wx2, because it was temperature, was 2 degrees Celsius. And what's the uncertainty of R? Because we treat R as a constant, the uncertainty of R, x3 in this case, would be just 0. 0 joules per kilogram Kelvin. I have to show the unit to make sure that everything is good, right? Okay, so this is our case. Now, the uncertainty propagation theory says, you have to look up the theory, how they developed it. It says, if I have the function f like this, and the function is is a function of basically a bunch of variables, x1 to x2, x3, x4, x5, whatever, up to xn, we have n different variables. In the case of ideal gas law that I gave you, n is 3, right? And if we have a case like this, the uncertainty propagation, which is known as W sub f, that's the uncertainty propagation of f, using a method that is called RSS method, root of sum of the squares, I'm going to write it down, will be this: sigma I goes from 1 to n, the partial derivative of f with respect to any x, xi, times the uncertainty of that xi, whatever that variable was, squared, like this. This is called the RSS method, root of sum of the squares. RSS, root of the sum of the squares. For example, in our case, this WF in general, what does that mean? Let me just expand this series so you get the point. Would be the partial derivative of f with respect to x1 times uncertainty of x1 squared plus the partial derivative of f with respect to x2 times the uncertainty of x2 squared plus the partial derivative of f with respect to xn times the uncertainty of xn squared, like this. For our case, we have the density, right? Then how do I find the uncertainty propagation for density? The uncertainty propagation for this density using the ideal gas law, it depends what kind of law you use. Using the ideal gas law would be the partial derivative of density with respect to pressure, uncertainty of pressure squared, right? Plus the partial derivative of density with respect to temperature, uncertainty of temperature squared, plus the partial derivative of density with respect to R, gas constant, R squared, like this. Because we assume that the uncertainty of R is 0, we're not using any values for the uncertainty of R, so this term basically becomes 0. And for our case, this just simplifies to uncertainty propagation of density using the ideal gas law. Just simply becomes just rho P squared plus rho T WT squared. That's it. Again, this is the RSS method for uncertainty propagation, known as the root of the sum of the squares. Okay, now that we know the theory, we want to apply it. We want to apply and actually see how that works. And then, after solving this problem by hand, we're going to use it on EES. So we're going to get the exact same values also on EES. It's going to be pretty interesting. So let's do that. Okay, so let's apply that theory on the problem we proposed at the beginning of the video. Okay, one more time. The average value for pressure was given as 100 kPa. And the uncertainty of pressure was given as 10 kPa. The average value for temperature was given as 20 degrees Celsius. We have to convert this to Kelvin because that's not going to work if we do ideal gas law with Celsius. And the uncertainty of temperature was given as 2 degrees Celsius. But because this is uncertainty is just temperature difference. It's equal to 2 Kelvin. So they are the same. So the uncertainty of 2 Celsius is the same as uncertainty of 2 Kelvin. Basically, they are the same, right? And but the average value you have to convert. You have to convert that to Kelvin. Now, what's the equation? The equation for density is P over RT. R, we established the fact that R is a constant. R is a constant because the uncertainty of R is 0. So I don't have to worry about it. So if I take the derivative of, let me move this here. I guess my page, my face is probably blocking what you see as the uncertainty of temperature. Probably this is better. Now I can see it, right? Sorry. Now, if I want to take the derivative of partial derivative of density with respect to, let's say, pressure, okay, so I just have to treat everything else as just a constant. So that would be 1 over RT. That's just calculus. I assume that you know how to take the partial derivative. And if I want to take the partial derivative of density with respect to temperature, then P and R are just constant values. P over R is just a constant value, and the whole thing just becomes the partial derivative of 1 over T. 1 over T, if that's the main variable, becomes negative 1 over T squared. That would be the partial derivative of density with respect to temperature. So, okay, so we got the partial derivatives. What's the next step? The next step is to calculate these values so we can use that RSS method. Your question is, okay, what am I supposed to use for temperature here or pressure when I want to calculate these values? Let's say I want to calculate this guy. What am I supposed to use? What you use here are the average values. That's the trick here. So the partial derivative of density with respect to pressure would be 1 over, what was R? R is 287 joules per kilogram Kelvin, right? Kilogram. Times the average value of temperature that was given in, of course, Kelvin, because you can't use 20 Celsius in ideal gases. So that would be 20 plus 273.15 Kelvin. That's it. I did a poor job showing this fraction, so let's make it look better. Okay, that looks better. You calculate this value. After you calculate this value, already, calculate this value, it turns out to be and you can, pause this video and you calculate yourself to make sure that I'm, giving you the correct numbers, but it becomes 0.00040, 1189, like this. And of course, this number has a unit. What's the unit of it? The unit would be the unit of density over the unit of pressure, basic SI units, because I even converted that kPa to Pascal when I calculated these values. And same case with the partial derivative of density with respect to temperature. So that would be this guy. That's the partial derivative, right? So that would be P over R. What was P? P is, you got to use Pascal here. The 100 times 10 to the third Pascal, the average values I'm using. R is just R, 287 joules per kilogram Kelvin, right? Like this, times negative 1 over temperature. Temperature was 20 plus 273 Kelvin squared. So it would be something like this. So this would be, this whole thing is Kelvin, right? Make sure the unit is Kelvin. After you calculate this, I already calculated this one too. I get a value of negative 0.00455. What's the unit? The unit is obviously kilograms per meters cubed over Kelvin. That's the unit. Because you took the derivative of density with respect to temperature. This is 4. Clean that up. Okay, that looks better. Okay, now we got everything. Now I want to calculate the uncertainty propagation for density. The uncertainty propagation for density would be, using the RSS method, would be the square root of the partial derivative of first this guy, density with respect to pressure, Okay. 0, 0, 0, 0, 1, 1, 89 times the uncertainty of pressure, which was 10 kPa, that is 10,000 pascals, this whole thing squared. I'm going to add the units also, plus the partial derivative of, with respect to temperature, negative 0.00455 times the uncertainty of temperature, 2 Kelvin, like this whole thing squared. That would be the uncertainty of density. Make sure that these units are correct. This unit is Pascal. Let's write it Pascal. This unit is kilograms per meters cubed over Pascal. This unit is kilograms per meters cubed over Kelvin. And of course, this is Kelvin already, so I can just keep it 2, and this guy is just Kelvin, like this. After you calculate this whole thing, you can pause this video and calculate this. The uncertainty for density happens to be 0.1191 kilograms per meters cubed. Now that I have everything, I can report the value of density like this. This would be the value of density. You use the equation, use the values that you measured, and use the average values, and use the uncertainties to calculate the uncertainty propagation, basically. And after you have that, you can say, okay, final density equals the average density plus minus W of density, right? Which means density equals, in this case, 1.189 from what I remember, plus minus 0.1191. This whole thing is kilograms per meters cubed. Problem solved. So now I calculated the uncertainty propagation for this problem. So I kind of zoomed out, so you can, take a screenshot of the whole solution if you want to. Now, this is how you calculate uncertainty propagation using RSS method. You can deal with way more complicated equations than taking those single partial derivatives become more complicated, right? So it's just calculus. You have to take the derivatives. Now, what if you have so many of these equations? What if you are, let's say you are testing a compressor. You're testing a compressor. You put, I don't know, some orifice plate somewhere. You are putting some pressure transducers, some thermocouples. You're measuring different things. You want to measure the flow rate using that orifice plate. You want to measure the pressure and temperature of the tank, or the pressure before the first stage of the compressor, after the first stage, whatever you're doing. And you're using a bunch of thermodynamics equations to, test the, the flow rate of this compressor, test the final pressure of it, test the amount of work that it can produce, whatever, right? So you're going using a bunch of thermodynamic equations. In that case, how are you going to incorporate the uncertainty of all these pieces of instrumentations that you're using? It becomes more complicated, and you're going to make more mistakes when you're taking those derivatives by hand. Here, I'm going to show you an easier method using EES, Engineering Equation Solver, that gives you the exact same numbers, and EES will do it for you in one click. So let's move on to EES and solve it. And you can pause this video to take a look at this solution. Make sure you write down these numbers. We're going to get the same numbers in EES also. Okay, here we are with a new code in EES. EES is Engineering Equation Solver. If you don't know how to use EES, I'll put a link in the description. I have a video on how to use EES. I mean, just as an introduction, so you can watch that video and then come back here and understand what's going on here. So basically, the first step in EES, I mean, I already showed the value of pressure. Let's just delete that and start from the very beginning. So the first step is just you go to options, you go to unit system. I'll do this from the very beginning because you need to know that what's going on. And you need to make sure your unit system is fine. Since we're using the ideal gas law, and in ideal gas law, I'm going to use the basic SI equations. I'm going to make sure that the units are basic SI. So pressure is Pascal. I'm going to use Kelvin, and I'm going to use joules. And so this is good to go. Now, the first part is just you have to just type in the values that are given. So the pressure was given as 100 kPa. Okay, 100 kPa, but I will have to convert this to Pascal. So I've got to go from kPa to Pascal. I do that. All right, cool. And next step is temperature. Temperature has to be Kelvin. So I got to use the convert temp function and go from Celsius to Kelvin. And the temperature was given as 200 degrees Celsius. That's pretty much it. If I want to use the ideal gas law by hand, I'm going to enter the value of R as 287 joules per kilogram Kelvin also. Okay, cool. That's it. That's pretty much it. So in the solution, when you want to calculate the density, I'm going to use two different methods to show how to calculate density and show you that, it doesn't have to be an equation. EES uses its own functions, the, equation of state functions, and like density, like enthalpy, entropy, whatever. And that uncertainty can even propagate into the result of those functions, which is pretty cool. So rho, using the method I just showed you, I called it rho 1. Is pressure over R over T, right? So P over RT, basically that's it. And if we just, just run this just to get that value that I showed you, there is an error function convert. Oh, yeah, I forgot to convert temp like this. Okay, so yeah, you run this and you realize, oh, this is the value I showed you. 1.189 is the value of this density that we're looking for. Okay, cool. But that's the average value. That is not the uncertainty propagation. How do I calculate uncertainty propagation? Here's the thing. You go to this menu here, calculate menu, right? And in calculate menu, there is uncertainty propagation. Uncertainty propagation, okay? It says what value is a calculated value. This value, rho 1, is the parameter that I am calculating using the measured values. We assumed that we had the barometer in the room and a thermometer in the room. Okay, these two were the measured values. And the next step is, okay, set the uncertainty values. You click on this button here, set uncertainty values. Now, there are two types of uncertainties. Uncertainty could be given as relative uncertainty, or it can be given as absolute uncertainty. Absolute uncertainty is the one that I recommend because the uncertainty that was given here was, in fact, absolute uncertainty. It said the pressure transducer, the uncertainty was 10 kPa. So you can type that value. The average value was this value, 100,000, pascals, and the absolute uncertainty is basically 1, 2, 3, 4, 10,000 pascals, right? 10 kPa is 10,000 pascals. So when you put the absolute value, they have the same exact unit as the original variable. Or you can put this value in terms of relative uncertainty. Relative uncertainty doesn't have a unit. If you divide the value of, because it's relative, divide the value of 10,000 pascals over 100,000 pascals, that is 0.1, which is the relative uncertainty. You can even give the value of uncertainty in terms of relative uncertainty. Sometimes it is useful, and sometimes it's not. For the most part, I use the absolute values. But if you want to do that, you do either. You can't just enter both absolute and relative, no. So in this particular case, the relative uncertainty becomes 0.1, because if you divide 10,000 by 100,000, you get 0.1. Look, if I click here, you see what happened? 0.1. That's the uncertainty. And here, 10,000. I would say 10,000. Same case for this. For this, for the temperature you go to do Kelvin. The uncertainty was 2 Celsius. But you are not going to convert 2 Celsius to 2 Kelvin, to Kelvin. 2 Celsius. That was already the difference of 2 Celsius is also the same case as, a difference of 2 Kelvin, right? So the uncertainty, we converted the average value from Celsius to Kelvin, 20 degrees to 293.2 Kelvin. That you should do that. You must do that. But you're not going to convert the uncertainty from Celsius to Kelvin. Why? Because temperature difference in Celsius is the same as temperature difference in Kelvin. However, if you are going from temperature difference in Celsius, you want to convert it to temperature difference in Fahrenheit, yes, then you have to multiply temperature difference in Celsius by 1.8 to get temperature difference in Fahrenheit. But that's not what we're doing here, right? So make sure that you're okay with these units and everything, because it can mess you up. So the uncertainty was 2 Celsius, because uncertainty is a difference, plus minus, is the same as 2 Kelvin. So I just type 2 here, right? And that's okay. So I set the uncertainty values that the problem gave me. If you click on OK here, you get the answer that you want. Look at this. This is the uncertainty calculated using uncertainty propagation method, RSS method in EES. EES, in fact, took those derivatives for you. Look at this. This is the derivative of rho with respect to P. If you remember, I got the same number here. Well, it doesn't show the units, but it does have units. The unit of this is kilograms per meters cubed over Pascal. EES also calculated the uncertainty of temperature, of density with respect to temperature. The unit of this is kilograms per meters cubed over Kelvin, and this is the exact same number that I got for you. So EES is doing that. This becomes very useful when you have so many equations, when you're measuring so many parameters, you're testing a piece of equipment. If you want to sit down and calculate these uncertainties, then it'll take a lot of time. Eventually, you want to find the efficiency of that pump, compressor, or whatever, and then the uncertainty will propagate into the uncertainty of that efficiency. There's something interesting here you can see. So first, if you look at this, let me highlight this. What you see here is the uncertainty. It says the density is 1.189, which is the average value, plus minus 0.1191, which is what we got using the RSS method by hand, kilograms per meters cubed. Also, it says 99%, 99.54% comes from here. It says the most of the uncertainty for this problem comes from the uncertainty of the barometer, not the uncertainty of thermometer. What it shows is that if you want to get a more accurate result in this test, measuring the density of the air in the room, if you don't have to worry much about the thermometer in the room. Maybe you should consider getting a better barometer with less uncertainty to get a better, more accurate value for density. That's what it says. Most of the uncertainty comes from the barometer. That's what it says. So this is pretty cool, and that's an important part. Now I'm going to show you one more thing here. You might say, okay, so this is for equations. EES uses a lot of functions to find enthalpy, entropy. I don't know. What if I want to calculate what if I, instead of using the ideal gas law, I use the EES model for density that uses the ideal gas law? So I'm going to call it rho 2. Rho 2 is the density of air. Air is the ideal gas model of air for EES. Temperature is T, and pressure is P. The P and T, and we defined. And what would be the value? So it's going to use the ideal gas law. We should get the same value, and we got the same value. These two values are essentially the same, kilograms per meters cubed. This is 1.188, which is the same as 1.189. They're the same pretty much. So that's the value that is calculated using the model that it has, right? Now, how can I use, the function to find the uncertainty? Same thing, nothing different. You go to calculate, you go to uncertainty propagation. Now, this time, you also choose rho 2. Rho 2 is also a calculated variable using the measured variables that we fed EES. So you go here, set uncertainties, and same thing. Well, you don't even have to change any of these. Keep everything the same. And it's going to use the uncertainty even for the built-in function in EES, and that comes handy. Let's say you want to find the entropy also of air, and you want to see the uncertainty in the entropy. See what happened here? Row 2 also, same deal. We got the uncertainty of it. I got the same value. This part is calculated, but EES is a built-in function. Can I use this for other things? Of course I can. I can use this for even entropy. I can say entropy of air. Let's calculate the entropy. That would be entropy of air when pressure is that pressure that we calculate, and T is that T. It is going to do it for you anyways. And then go to uncertainty propagation, calculate uncertainty propagation, and this time choose S also. You have to choose these guys. Now this uncertainty values are still the same. When I click OK, it will even calculate the uncertainty of entropy for me. This is one potential unit. That's because, let me just run it here. So fix that potential unit. It's because this value would be joules per kilogram Kelvin. So make sure that you don't have any uncertain, not kilogram equals Kelvin, kilogram dash Kelvin. Okay, so now it's good. Now let's go back to uncertainty propagation, uncertainty, and everything's good. So uncertainty is okay. Now I have, it says for these measurements of the pressure and temperature in the room, when you want to calculate the entropy, let's say the entropy is going to be off by about 29.53 joules per kilogram Kelvin, basically. So it even calculated the average value of entropy. That's the entropy of the air in the room, 5682 joules per kilogram Kelvin, and the uncertainty of it. How cool is that? Okay, so it's pretty much it. Another interesting thing is that when you look at, let's do this one more time. So if you take a look at the uncertainty of these guys, entropy, density, whatever, these two are the same because EES is using ideal gas law also. So we use ideal gas law here by hand, and EES is using the built-in function. So, you know, the same numbers. Everything is pretty much the same. For entropy, EES is using some sort of built-in equation of state. And using iterations, basically they solve those equations of state. Now, the interesting thing here is for entropy, however, you see temperature actually plays a bigger role compared to density. Like it is 5.38% of 5.38% of uncertainty of this entropy comes from the temperature. And 94.62% of it comes from pressure. So looks like entropy is more sensitive to temperature in this case, right? As opposed to density that was not that sensitive to temperature. It was more sensitive to the uncertainty of pressure. So these are cool things that, you know, you can consider by just looking at it. And it's a very cool thing that, you know, EES has. All right, this is pretty much it. I'm going to go back to, hope you learned something from this you know, video. This is the code. If you want to pause it and write it down for yourself, make sure you use basic science. There's nothing to it. I mean, that's pretty much it. Okay, so I hope you learned something from this video. And again, make sure you subscribe to this channel as I upload more videos this summer. Have a great day. Thank you.